I'm going to do is actually just go to, so there's been several versions of these slides, and these ones have got a couple of little minor mistakes in, which I'll go through. So anyway, we're talking about the crypto keys. So when you're generating cryptography keys, you want to be able to have random numbers that are not reproducible or can be guessed. We were going to be talking about random numbers in a minute and how they can be generated. And so we for crypto keys, we need some really decent random numbers that cannot be predicted. Secure boots for sessions during secure boot. We need to have random numbers to ensure a robust system. Nonces, number used once, and sessions, the same thing applies, and authentication for that. So not going to go. Okay, so here we go. So this is the classical randomness. We have sort of three main ways of generating random numbers currently. We have the pseudo-random number generator. Oh, sorry. I haven't done this before. So yeah. Okay, so yes, you've got the PRG, which is kind of like an algorithmic type of a way of generating random numbers. You have the ring oscillator. Oh, okay, does it like that. So you have the PRGs, which the pseudo-random number generators, which can be used to generate what looks like random numbers, but actually quite predictable if you know the seed. Ring oscillators using impurities in circuits and instabilities to generate random numbers. What's wrong?
You're turning your head.
Oh, right. A bit higher. Okay, 1, 2, 3. Okay, ring oscillators, yeah, using instabilities in circuits to generate your random numbers, and then noise sources using random environmental noise sampled. An example could be just a microphone without a microphone. You've got lots of background noise there. That could be quite random. But a lot of this is the problem with this is it's quite deterministic. Once you know with the random numbers, you can with the pseudo-random number generators, you can quite often predict what the next value is going to be, especially if you know what the seed is. Circuits such as the circuit-based random number generator, the imperfections in the power supplies can cause random numbers to come up, or fixed numbers to come up in your random stream. I've definitely seen that happening before. They tend to be quite biased as well, sort of heavily kind of one way or another. But they're vulnerable to observation. And one of the problems that you've got with random numbers is you can't really measure them. We'll go into this a bit later, but it's not like you can just look at a number and go, is that random? It's based on quite a large number of samples, but we'll get into that a little bit later. So these are sort of problems that we've got at the moment. Generally speaking, you can predict what the value is to a certain extent. So what can we do here? So we can enter the world of quantum and the physical source of unpredictability. So in the world of quantum physics, you can really achieve true random numbers. I'll go into how we do that in a second, which is the non-deterministic measurement. It's not algorithmic as well, so there's nothing you can't predict anything. External to FPGA, that just means that, yeah, the source is coming outside of the FPGA, but quite often that always happens anyway. You might be using an external oscillator circuit or source. All right. Okay, so we're going to move into the world of the classical bit versus the qubit. So qubit is the quantum equivalent of the classical bit, where we have 0 and 1 in the classical world. And we all know about zeros and ones, a binary 0 and 1 in VHDL, in FPGA design. In qubits, it's slightly different. Initially, it is a value of sort of 0 and 1 when you use it. And then you can put it into this state called superposition, where you simultaneously have 0 and 1. And then when you read it, it collapses down to a random value. So that act of collapse is what produces the truly random value. This is our block sphere representation of a qubit. Don't really need to understand this, just be aware that it exists. This is the general way of drawing a qubit. For the basics of what we're talking about now, you've got effectively poles, the North Pole and the South Pole. North Pole is 0, the South Pole is 1. So when you read it, you'll be reading those points there. When the thing is in superposition, you can imagine that sort of rotating very quickly. And you could be anywhere inside here where it's simultaneously 0 or 1. When you read it, when you measure it, it then becomes a definite value of 0 or 1, and that acts as the truly random nature. So the idea is that you start in a known state. Psi is either 0 or 1, and then you use a thing called a Hadamard gate that puts the qubit into superposition, and then when you measure it, it yields the 50-50 outcome. So the probability of 0 and 1 are both a half. So I've put something in a kind of visualization here for those who can't really visualize quantum. I've used a sort of a heads and tails analogy of a coin. You can start with the coin on the table and it has a fixed value. That's the initial qubit resting state. When you put it into superposition, it's effectively like spinning the coin. So when you look at the side of it, it sort of simultaneously looks like heads and tails. And then when you measure it, it's effectively like slamming your hand down on the coin, giving you a value which is truly random. Okay. So what do we actually do to get these random numbers? How do we actually talk to a quantum computer? Because a quantum computer is completely different to the way that we see computers. But luckily, IBM have helped us out here. So IBM have several quantum computers which you can use either in a simulation type mode or use the real system. You can access the quantum computer using a sort of Python plugin called Qiskit. And it allows you to access the quantum computers, instantiate as many qubits as you need, request as many samples as you need, and it will send it back to you in a simple text string, which you can then process and use. So IBM provides access to real quantum processors over the internet. At the moment, they've got 3 live from this morning. Circuits are submitted remotely and executed on quantum hardware, obviously. So that's because you run a bit of Python code with the plugin. It talks over the internet to the IBM quantum server, and that will then do the necessary bits to talk to the quantum computer and then come back with its with those true values. As I mentioned earlier, yes, you can build the quantum circuits, anything you like. What we're doing today is probably the most basic thing you can do in the quantum world, probably equivalent to the hello world type thing, but in quantum world. You can simulate locally as well. IBM provides you with a simulation environment where you can test all your code before you actually use it on quantum computers. At the moment, they've got you can join up. I've got the links I can show you later if anyone's interested. You can join up. It's free. I think you get free 10 minutes a month, and you can then pay something like £1.60 for a second of use. Each request I do seems to come back as a second. I think a second is the minimum access they sort of charge for. But I'm still well within my 10 minutes, even playing around with this quite a lot. Oh, here we go. So this is a bit of real code for you. So this is the basics of what we need to do. Has this got a pointer on it at all?
It has, but it gets absorbed by the screen.
Oh, okay. No worries. I'll come over here.
Finger instead.
You might not be able to see it now. Okay. So yeah, there's a little function here to pull in the Qiskit libraries, create a service. and then select which back end that you want. That's the important bit. Simulator is false. You set that to true, then you end up using the quantum simulator and think everything's great, but then it's not actually giving you any random numbers. What you'd have here is you create an instance of a quantum circuit. You say you want one quantum circuit. This bit of code here does the Hardeman gate on the on that particular qubit. So that puts it into superposition, and then the QC.measure_all that then reads the quantum bit, which will then be truly random. So this is the basics of what we do. Again, I can provide the code if you need it later. Okay, so this is a little bit wrong. This was right, but it's not quite right. So I will kind of re-explain. This kind of makes sense. What you've got when what we do is because we're generating a dice for the demo. We need three binary values from 0 to 7, and we throw away 2 values that we don't need. And initially, I thought this would be good enough to, if you get a 0 or 3 ones, you re-roll that. But any value between 1 and 6 is accepted as a real dice value. That apparently, I found out yesterday, may put bias on your circuit. So I've redesigned it now. So the code's all updated now, so that we used values between 0 and 5, throw away values 6 and 7, but we add 1 to the values of 0 to 5. That apparently removes the bias. Is everybody okay with that? Yeah. Oh, well, we're here already. Okay, so this is a demonstration. So what we'll do is I'll take you over here. This is a kind of a work in progress at the moment. So what we've got here, actually, I will just bring up the block diagram there. I can explain exactly what we've got. We've got a Sonata board here. This is made by a company over in Cambridge called Low Risk. It's got a Cherry core on there, and Chariot as well running on top of that, or Chariot operating system, very secure software stack. And I've got my little application running on top of that. So the idea is this. I know we've got 2 Raspberry Pis here. These are really primarily to drive the cube display. This is our version 1 of the cube. Version 2 is being built at the moment. That is actually all screens, or potentially 6 screens, but we'll use 5. Will be driven by an FPGA. That's been a bit of a task really to get that working. But this is our version 1, which is driven by 2 Raspberry Pis. You have the master Pi here, which drives the top screen, and the slave Pi that drives those 2 screens there. The idea really of the master's Pi, apart from driving the cube, is to have a quantum server running on it. So the quantum server will talk to the quantum computer, request the random number, and then it will then send the random number back to the Sonata board. And it will also broadcast that to the other Pis that have got display servers running, including its own Pi, and that will update the screen there. So the way of communicating, at the moment we haven't got a Cherry TCP/IP stack. We're working on that at the moment. So at the moment I've got to run the Pi server on the the quantum server on the Pi. So at the moment, the way we communicate, we've actually got the Pi powering the Sonata board. But because it's that's also a USB serial connection, this actually acts as a client and pumps serial messages through to the server, which is just looking at the serial port there. It's very simple, and it's just saying, requests a binary, a dice value. The dice value comes back. And then that is then put on the LCD display on here, which you may not be able to see. And it also goes onto the screen there. I think that's everything. Yeah, there we go. So that all ties up with this. So nice. We've got the button on the Sonata board. That then goes up through the RISC-V core on the FPGA, then up through the operating system, up to the application. Application goes, oh, okay, I need to request a number. So it then comes back down through here, across the serial port, across to the master Pi, into the quantum dice server, which then requests the number from the quantum cloud, and that comes back, gets passed through here, back up to the application. The application sees what the number is, and then sends it to the LCD display. Furthermore, it will send it to the Cube display driver, which will then run to the servers on the Master Pi, but also transmit to the servers on the Slave Pi. Right. So all we have to do is press that button, and yeah, I'm really worried about moving this in case it all powers off, but you can probably see there that there's a shuffling going on the LCD. That is, we're waiting for the quantum server to, the quantum computer to come back with a random number, which hopefully shouldn't take too long. It's come back with a number 5, and you can see the screens have updated on the dice display to display the random number, and we can do it again. This highlights one of the problems which I'll talk about next, about the latency of getting the number from the quantum computer. It takes about 20 seconds, but it all depends on how many people are using the quantum computer at the time. That's the number 6, so you'll see the screens are updating to support the 6. So yeah, not very exciting, but it does quite a lot of stuff. So right, the NIST statistical test suite. So I mentioned earlier that it's quite difficult to measure random numbers, but the NIST have developed this statistical test suite, which you can download. I've got the link to that if anybody's interested, and then you can send a bunch of random numbers to the test suite, and it will give you some information on those random numbers. It doesn't just say, yeah, true, this is random, this is not random. It just gives you lots of extra information, mainly statistical. How many zeros and ones have you got? What's the kind of balance of it? Are there any repetition? Is there any predictability in it? Is there any bias in it? But it's a good way of doing it. Ideally, it requires quite a lot of samples. I think when I read about it initially, it was saying about 1 million samples. It got about 64,000. I didn't really want to overload the quantum computer, and at the time I thought I was paying £1.60 per transaction, so I didn't really want to ask for 1 million because that was going to start to get a bit expensive. But I could have run it in simulation mode, but there's always a difference between the simulation mode and the real thing. Oh yeah, limitations. So at the moment, every time you request a binary number, it takes about 20 seconds to come back from the quantum computer. You can get around that by you can request a certain number of random numbers at the same time, and so you can get a whole batch that come back. And in fact, I've written software to handle that. So what we do is we request, say, 10,000 numbers, and we store those in a great big text file. And as we use them, we decrement the text file, and as we get near the bottom, it requests more numbers and sticks those in the text file. That way we can run our system even if we haven't got access to the quantum computer. We'll always have a buffer of quantum numbers, and because we've got them actually on the text file or in memory or some kind of fast access, we can get over the latency issues. However, there is a problem with the fact that that might not be truly random. If you request a certain number of random numbers and they all come back, and then later on you request more random numbers and they come back, then those random numbers are not necessarily following on from those random numbers, because we won't necessarily get the same qubit, and there can be other people using the back end, other people using the qubits. So yeah, it's not an ideal one, but it allows you to kind of grab a whole bunch of numbers and store them locally. The cost access, as I said, it was about £1.60 a second. There seems to be a minimum amount that you can, if you do one access with requesting 1 qubit, it comes back as 1 second. If you say 10,000, it comes back as 1 second. I haven't tried any more of that more yet. I still don't know what the limits are. But it's something that's worth thinking about, especially if you're just constantly trying to get random numbers. The costs will eventually start to accumulate. Service limits, yeah. You're limited really with the number of quantum computers that are there at the moment. Like I said, I've got 3 when I last looked, and it's not really clear how many people are using them. But when you try and talk to the computer, you can request the lowest queue. But you never know what, even though there's a queue, you don't know how long everyone's going to be taking on the computer. So there's a little bit of a limitation there with, how long is it going to take and how many people are using the computers and if they're going to be taking the system down. The not continuous stream is the thing that's the most important here, is that if I had a qubit, my own qubit, and I put a Hadamard gate on it to put it into superposition, I then read it, I would get a value. If I did that again, I'd get another value. And if I kept doing it again and again, that random stream would be truly random. However, I don't really know what goes on under the hood at the quantum computer in terms of how they take everybody's accesses and how they kind of process everybody's accesses. But it may be that if I request 1,000 numbers from the quantum computer, I don't have that qubit for 1,000. I might have it for a period of time, then that qubit's used by somebody else, and so those random numbers that I request may not necessarily follow each other. But you know that each individual number is truly random. But however, you can't just take a whole stream. You cannot just assume that you've asked for 1,000 numbers that they're going to be one after the other from the same qubit. But that's something you could talk to IBM about. That's one of the future things that I would probably consider doing. If I asked for 1,000 samples, I want that qubit for 1,000 samples to make it truly random. Security considerations in transport. This was something I was a bit concerned about when I thought about this, is that you're sending all these random numbers over the internet. That doesn't seem like a very sensible thing to do for the stuff that you're going to be using in security. I did think that you could just say, right, send the whole random stream. No one's going to know which random bits you're going to take from it. And I thought you could randomly take random numbers from the random stream, and that would still be random. That's not random. So I'm not sure how to deal with the security considerations, but probably wrap it in its own VPN or something. There could be some way of securely transporting it. I'd probably break it up into bits and break the stream up into bits and send different parts. Therefore, it would probably be very difficult for somebody to put that back together again, unless you knew the sequence of how you put it back together again. So the future potential. Yeah, the premium quantity entropy option, that's what I was saying, when you could talk to IBM and say, if we request 1,000 or 1,000,000 random bits, we want them to be truly random. We want to have access to that qubit for that length of time, and we don't want anybody else using it because that will affect the random data. The secure end-to-end entropy, so that's some method of sending the entropy from the quantum computer to your storage unit. Sole use of qubit per session, yeah, that ties up with the premium quantity quantum entropy option. Large number of bits request size, yes, at the moment it suggests about 10,000 is the limit, but it would be nice to be able to say, I want to request 1,000,000, and then you can get exactly what you want then. Also, I'm not 100% sure the cost. At the moment, I can get up to 10,000 bits with for 1 second. But I don't know what would happen if I then made that 100,000 bits. Is it still going to be 1 second, or is it going to be is suddenly 100 times that? Large number of bits request size, specialist hardware to reduce noise. Okay, so this is the one problem. Quantum computer, yeah, theoretically gives you a random number, brilliant. But the problem you're going to have is you've got classical technology that's surrounding the quantum computer. So that might still be introducing some kind of noise into the bit stream. I haven't seen any noise on my analysis so far, but I've only used about 64,000 bits in my analysis. I haven't used a huge amount of data. So yeah, I would have to talk to IBM about that and find out how how do they get around the noise being introduced into the random number generation. Quantum on chip, eventually that's going to be nice. You know, that would be something that you can actually put on the same board as your FPGA. Nice little quantum, you know, a qubit in there. And but that, I think we're way away from that now. But that would get away with, that would certainly remove quite a lot of the problems. You wouldn't need to worry about transport. You wouldn't need to worry about cost, apart from the initial cost of the quantum chip. Okay, so Cherry TCPI sticks. So this is more of the demo thing. So my demo over there, I'm using the Raspberry Pi for. I just want to. Have we got much time? I've just worried about 2 minutes. Brilliant. Okay, so Cherry TCPI stack for embedded and secure edge. So at the moment, on the Cherry, we haven't got a TCP/IP stack for the demo. It'd be really nice when we get that working, because then I can get rid of the Raspberry Pi for the quantum server and have everything running from the FPGA. But we're just not at that point yet. I was hoping that I could probably write something inside the embedded system to talk to the quantum, but I've been a bit busy over the last few weeks with other stuff. And then there was another point as well, which was going to be the Linux core. Once they develop a nice little Linux core that will run on Cherry, then I can run all my Python scripts that I'm running on the Raspberry Pi on the Cherry board. So that's my two. Oh, that's it. Okay, so yeah, any questions, or I'll just call it a day? Right? Yeah. Hello.
Yeah, it's just an observation rather than a necessary question, but
Yeah.
just tying up your presentation and what Ian just said.
Okay.
IBM, their quantum computer,
Yes.
is in scope of CRA. So therefore, have a chat with them and see what they're doing, because you might lose access in a year's time.
Okay.
Well, you won't be able to access it from Europe. Well, no, it's still in scope.
Sorry if this is a silly question or if it doesn't have a quick answer, but in your presentation, you seem to say that a subset of a random sequence might not be random, and intuitively, I find that hard to understand.
Oh, I know. I'm not a random number expert by any means, and I'm always making assumptions that, oh, if you have a random stream that's generated, each of those bits is random, and you've got a random stream, why can't you just randomly pick 5 bits there, 5 bits there, 5 bits there, and it still be random?
Yeah,
but,
yeah, this was.
But I've been told that that's not random, because you're randomly picking bits, but then you could be picking ones randomly, and then you could have a whole train of ones because of where you picked it from. Because unless you pick it, maybe if you pick it the next number from the random number generator itself, it might. I don't know. I found my head getting around that a little bit difficult as well, because you thought, well, it's already random, so come on, surely you can just randomly pick it. But no, I'm afraid that you're stuck with that. Unless you can find some math genius that can explain it better. But
Oh, and one more question. You were talking about noise. I suppose noise is a problem if it's predictable, right? So if you had truly white noise,
in the classical world, yes, you can. If we had I've seen this before with oscillator circuits. I wanted to evaluate some of the random numbers at a previous company, and we had a very huge amount of numbers. And I got one of the guys to write a little script to go through and try and find predictability in there. So, go through and find chunks of numbers, and you could see them. You could see the same number in that small stream that we had, and apparently that those numbers can identify the source of the random number who's producing it. Because each piece of hardware is generated differently. One company will do it like that, and another company will do it like that. So it's almost like a fingerprint that you can use to determine who's generated your random number.
I suppose that's the essence of a physically unclonable function, really, isn't it? That you can't predict it, but it's unique per piece of hardware that you've got.
That's right. Yeah. I mean, I can prove it, but I cannot predict it myself, where those numbers are. But I probably could if I sat down and worked on it. There's going to be some kind of, if you know what the noise is it 50 hertz signal, you can probably work out how often, 50 times a second, you're going to start to see the repetitions potentially. But that's for future study. And anyway, yeah.
Thank you.
Oh, that's all right. No worries. Anything else? Oh.
Thank you. Perhaps following on from that, I was just wondering, you mentioned at one point that there was bias when you removed the zeros and the sevens from the
Oh yeah,
EQ.
the bias. Yeah.
What did that mean?
Sorry. What does what mean the bias?
Yeah, how was the bias introduced and how was it removed by changing which numbers you threw away?
All right. Well, yeah. That some of this random stuff is beyond me really, but I thought taking values of 1 to 6 and throwing away 0 and 7 would be all right. But I was chatting to my maths friend last night, and he said, no, that's not right, because you've got to, that will introduce bias. And I said, I can't visualize it. And he said, no, trust me, it does. The best thing to do is use 0 to 5. That's the way that everybody does it in the industry, and throw away the 6 and the 7, and then add 1 to it. Yeah, that's all I can say, really. I can't give, you're going to have to ask somebody a bit more mathematically minded than me about that. Yeah.
Further reading then.
So, Assad?
Yeah, thanks, Phil. That's a great presentation. So my question is that theoretically, the quantum computer will give you random numbers, but has anybody actually checked that the IBM quantum computer is actually random?
Oh, I've checked it with the small amount of samples I've got.
But I mean, a proper sort of, tens of millions?
Yeah, I'd need to have more samples.
No, not you, but anybody else. Is there data that sort of?
Not that I've seen.
Is it?
Well, I haven't dug that deep, but
Okay.
I can certainly have a look for you. Yeah.
Just to follow on that question, so you mentioned NIST, SP, and a bunch of numbers. So is that the standard for measuring how random a number is?
Oh, NIST. Yes. So we use that at Airbus for running tests against our random numbers that were generated. We also wrote our own scripts to do some of our own analysis. So, checking for sections that are repeated within the random numbers, but certainly the NIST is a sort of industry standard.
Thank you.
I think we're going to call it a day on that, because I'm running into the next guy's talk. But I'll leave the, oh yeah. I'll leave the demo running over there. Just press the button and it will generate a number for you. Sorry, one mess.
Thank you. Cool. Okay. Oh, you go. Oh, no, don't listen. Go ahead. No, hang on. No, I'm not trying to stop sharing. I want to deal. Thank you.